Welcome to the Roland High School IB Physics Summer Podcast number 5. Today's topics are solar radiation, albedo, and energy balance. Okay, welcome back. Before listening to this part of the podcast, be sure you have read SOCOS, the section on solar radiation. It's on pages 436 to 437. If you haven't read it, pause this and I'll wait patiently for you. Solar radiation. The sun emits 3.9 times 10 to the 26 watts of energy. That's like a huge 3.9 times 10 to the 26 watt light bulb out there in space. The average distance between the Earth and the Sun is about 1.5 times 10 to the 11th meters. In other words, that's the radius of Earth's orbit. As energy leaves the Sun, it spreads out in all directions, like the surface of a large sphere. And if you're at a distance, say r, from the Sun, the power is spread out over the area of a sphere of radius r. You probably know that the formula for calculating the area of a sphere is 4 pi r squared. So the intensity, or the number of watts per square meter of sunlight that reaches any point in space, is going to be equal to the power output of the sun, again that's 3.9 times 10 to the 26th watts, divided by 4 pi r squared, where r is the distance between the sun and your location in space. So if we wanted to predict how many watts per square meter of energy is reaching the surface of the Earth, we would take the power output of the sun, again that 3.9 times 10 to the 26 watts, and we divide that by 4 pi times the distance between the sun and the Earth, which is 1.5 times 10 to the 11th meters, and we'd square that. And that quantity that you get when you divide the power by that area of the sphere is called the intensity, and the symbol for intensity is capital I. We'll be revisiting the same formula again when we talk about sound. If you'd like to calculate the intensity of the sunlight reaching the surface of the Earth, you take the power output of the sun, 3.9 times 10 to the 26th watts, and divide that by the quantity 4 pi times 1.5 times 10 to the 11th meters squared. And when you do that, you get about 1400 watts per square meter. So at the distance that we are on Earth from the sun, the intensity of sunlight reaching the top of our atmosphere is about 1400 watts per square meter. Okay, just to recap, intensity is a power per unit area that is received. In other words, intensity is how many joules of energy will strike an area of 1 square meter in 1 second. So 1400 watts per square meter of sunlight reaches the top of the atmosphere, but that's not the whole story. Not all of this energy reaches the Earth's surface. Suppose we wanted to calculate the energy that the Earth receives per square meter from the sun. Even though about 1400 watts per square meter reaches the top of our atmosphere, even before we take albedo into account, which is something we'll talk about later, the average power reaching the Earth is only 1/4 of that 1400 watts per square meter value, or about 350 watts per square meter. What's going on? How can that be? Well, the Earth's a sphere. But when the sunlight reaches the Earth presents a circular target. As we'll see, the surface area of a circle with a radius r is only 1/4 that of a sphere with the same radius. As you probably learned in geometry, the surface area of a sphere can be calculated by 4 pi r squared. And I'm sure you also know that the area of a circle can be calculated by pi r squared. So again, the surface area of a sphere is 4 pi times the radius of the sphere squared, but the surface area of a circle is pi times the radius squared. So if you have a circle and a sphere of equal radius, the surface area of the sphere will be 4 times that of the circle. So even though the Earth is a sphere, the cross-section that it presents to the sun is a circle. Therefore, the area of the Earth receiving solar energy is only 1/4 the area of the total Earth. And we're going to find out that the total Earth is radiating energy back to space. So we have this 4-to-1 ratio that we're going to be talking about later on. So you can see that even though there are 1400 watts per square meter of energy reaching the Earth, by the time we divide that by 4, we'll see that the average intensity of sunlight reaching the Earth spread over the whole surface is one-fourth of that, or about 350 watts per square meter. Our next topic is albedo. If you haven't read about it yet, go on back to your Sokos book and read page 437. Not all surfaces absorb energy equally well. If you place your hand on a black car that's been sitting in the sun for a while, you're going to feel that it's going to be much hotter than if you had touched a white car sitting in the same location. Why is that? Well, the white car reflects more of the sunlight back, and therefore less of the sun's energy gets absorbed. The ratio of the power scattered or reflected away to the total power incident on a body is called the albedo. Another way to say this is albedo is the fraction of the energy reaching an object that gets bounced away, that doesn't get absorbed. So an albedo of 0 means that no power is reflected or scattered away, therefore all of the power is being absorbed. So a very, very black object might have an albedo close to 0, meaning that light's not being reflected away from it, it's all being absorbed. On the other hand, an albedo of 1 would mean that all the power is being reflected or scattered away, and therefore none of the power is being absorbed. So light-colored regions of a planet, say snow or clouds, have a high albedo. Dark-colored regions of a planet, say forest or ocean, have a low albedo. If something happens to a planet causing its albedo to increase or decrease, that can increase or decrease the amount of energy that's being absorbed by the planet, and of course, that can have some effect on the temperature of that planet. Energy balance. If you haven't read about energy balance, head on back to your Sokos book and read page 437 and 438 about energy balance. We've already seen that a body such as the Earth can take in or absorb and give off or radiate energy. If a body takes in or absorbs more energy than it gives off, then its temperature will increase. On the other hand, if a body radiates more energy than it absorbs, then its temperature will decrease. Okay, a little math. Since intensity is power per unit area, then if you want to calculate the total power that an object is receiving, you need to multiply the intensity by the area, P equals IA. If you take albedo into account, then the formula changes a little bit, and we have P is equal to the quantity 1 minus the albedo multiplied by IA. And if you do the math for the Earth, the albedo of the Earth is about 0.3. So 1 minus 0.3 is 0.7. That means about 70% of the energy reaching the Earth gets absorbed because 30% is reflected away. And if you take a fourth of that, because of what we discussed earlier about the Earth being a sphere, you divide the 1400 watts per square meter that the sun sends to us and divide that by 4, and you get 350 watts per square meter. You take 70% of that, and the average sunlight hitting the Earth, if you over the whole surface of the Earth, realizing, of course, that half the Earth's dark at any time, but if you average over the whole surface of the Earth, the average intensity of the sunlight reaching the Earth is 245 watts per square meter. The power radiated back to space by the Earth can be calculated using the Stefan-Boltzmann law, and that power is equal to sigma A T to the fourth. I would highly recommend that you study sample question 3 on page 438 to get a good example of how an energy balance equation works. Well, that's it for podcast number 5. Podcasts are a one-way communications medium. People learn best through two-way communication. You can turn our podcast into a two-way communication medium by asking questions. Send your questions to me by email, or you can post them as a comment on our CAS manager. See ya!